Hello everyone. Thank you for coming for this session on chemical and electrochemical and gas sensors. I will co-chair this session with Stephane. So we have several presentations, and we will start with our invited speaker, Bérengère Lebental from Gustave. So Bérengère will give a talk on water and air quality monitoring with multi-parameter chemical sensors. So managing and non-idealities program to film. So Bérengère, you have 30 minutes for your presentation, so 25 and 5 minutes for discussion. Please.
Thank you, Hamida. Can you hear me via the room or the microphone? In the case, on the microphone. So welcome everyone. It's an honor for me to start the session on chemical sensors. I'm going to talk to you about both air and water quality monitoring because these two topics are very a lot of things in common. And I did something I thought very useful is talk about all the problems that we get. Not say everything is flashy and works, try to give you some sense about the problem you will encounter when you go to see an application and some idea about the solution and how the company can keep working and just try to make it work. So just a couple of insights into the challenges we're facing in air and water quality monitoring. As you know, already a lot of people suffer in the world from water scarcity. For instance, 700 million people, and most of the countries in the world are already under water stress. And of course, everyone knows it's going to get worse with climate changes. If you consider air pollution, we are at 7 million deaths per year attributed to air pollution. So we've got to do something. This something people want to do. What they want to do is to do dense monitoring of air and water quality. This one that your speakers say is the water analysis. It's center everywhere. You want to be able to monitor locally at very local scale water quality because you want to make good decisions. Example, this is a map of Paris from the sky, and this is a map of the air quality monitoring station in Paris. This station is 50 to 100 kilometers, and of course you can't afford this everywhere. And actually, when you talk to people, what they would like is to have this information for every school, every preschool in Paris. So you see the number multiplies, even every classroom, and what you want is a 100, 500 euros IoT device. This is not possible today. So what you do is you do a global index. You have a range of data, you have a global value. A very practical example where it would be useful. During COVID, you would have loved to have a CO2 sensor in the room, like in this room, like a CO2 sensor, how to ventilate. During COVID, it was not possible. It's not possible except in very rich schools and rich college. So why I'm saying it's not possible is because the sensors, when you enforce them, they don't work very well. There was a same discussion during the tutorial by Corinne, but these are very recent paper, and you see the comparison and performance of gas sensor in the lab and outdoor. And all these dots are device reported in the literature. And in the lab, the sensor they work awesome, they work perfect. And then when you look at the R2 between predicted and measured value, it doesn't work anymore. Like it's not even, it doesn't work so well. It just doesn't work. Like you get R2 at 0.5, 0.2, it's really terrible. And if you look at the literature, you have the same paper every couple of years. It's the same paper, the same review. Just by chance, I found a paper from Dallas about this exact topic. Actually, I was considering buying this system in our university, and they do comparison. This is in Dallas, in one of the hotels in Dallas, and they compare a lot of sensors from the same manufacturer. And the story is basically there are a lot of sensors not calibrated. And the O3 sensor, the ozone sensor, work, but you have one device out of 10, maybe two devices out of 10 that do not work. This is a commercial product, something that people are selling. And I have one example like that, the system just doesn't work. This is one problem with air quality. The problem is a bit less prevalent for water quality. If you buy a pH or chromium sensor for water quality monitoring, it sort of works. It's just pH and chlorine. And actually, in the field of water quality monitoring, you want heavily use parameter sensing. So this is the opportunity for me to introduce the NOTUS project. This is a European-Indian project, a collaboration between EU and India to develop water quality sensor at variable cost that can be deployed into use cases in India. So during this project, we have 5 different cases across India, and we want to deploy a technology there for water quality monitoring. And when you look at this use case, you see they are very differentiated. For instance, that one, for water city management, they want chlorine, pH, conductivity, arsenic, and fluoride. If you go to this use case, which is a distribution of water to tanker, which is very common in India, they just want chlorine and some sort of water quality index. If you go to irrigation application, you want to get conductivity, sodium, iron, carbonate, and so on. Hola, okay, so it's this time. Groundwater water monitoring, they want arsenic and fluoride for the same reason, it's actually variety. Or if you go to wastewater application, you want nitrate. So this is a very diversified, and this is for India. And if I go to France, people will say, they want something else. And if I go to the US, you guys tell me something else because you don't have the same pollination system, the same infection system. You don't look for the same species. So you want a device that are multi-parameter and resilient to interference in real conditions. So what a lot of people actually are doing is they do sensor array. So this is the main solution that I've seen today, to do a sensor array with redundancy. And people call it often electronic signs and losses. So there's a bunch of slight difference in the structure, but that's what it ends up with. It's sensor arrays. And the idea is that what people do today on a practical basis, when you buy a sensor in water or air, you buy an assembly of devices that people are like punching together. And if you want 10 parameters, you pay 10 times the price. And that's just mathematics, 10 devices, 10 times. There's no redundancy. It was managed device failure. What we want to do is to have a sensor that are multi-parameter by design. So basically, what you want to do is an array of sensors. Like you have, for instance, here you have 5 different parameters that you can monitor because you use 5 different materials. And because it's so compact, you can put redundancy. So like here, you have 5 devices of the same type. So this system, you have this chip. So it's a chip microelectronics, it's a chip. And then the rest, you pay once. So by design, it's a multi-parameter sensor that will be at the cost of a single sensor. So typically 1,000 euros there, and you can even hope to get it at smaller prices if you can make volume. So what I will speak to you about first on water quality monitoring is an example of that. But I'm sure a lot of you have an example of that for research or something. This is our example for water quality monitoring. So this is our system. This is 20 centimeters by 3 centimeters. So for locals, it's a bit more than 1 inch in diameter. And it's designed like this because it can go into pipes. This is the head of the sensor. So this is replaceable. For water, you need a replaceable end because water is super aggressive. You need to be able to keep the electronics for years and to replace the head. And then the magic happens here, which is the silicon chip, which is 1 square centimeter. And on this chip, you have 20 different devices into 4 columns of 5. And on this chip, you have 2 types of ink. One ink, which is pristine sensor. So this is a network of carbon nanotubes. So you see a carbon nanotube there, and you don't see anything on the side wall here. And we have functionalized carbon nanotube. We take this polymer, we mix it with the nanotube, so we get functionalized carbon nanotube sensor. And you see here, you have a lot of material. You may see that you have materials wrapped around the nanotube. And because it's super compact and it's electronic, you can also improve the device a physical sensor. Here, 2 temperature sensor and 3 conductivity sensor. So you may say, okay, it's just 2 parameters. Yes, we are right now building a platform for 2 parameters because we need to have a stable platform. And once we get 2 parameters, if we want more parameters, it's not a big deal. It's not a big deal because we have actually a bank of materials that we can mix the nanotubes with. And so we have a family of polymers. So it's actually a patent that we got from 2017. And the idea is that basically you make a polymer chain with carbazole or fluorine, but you graft specific sensors onto this thing. And these are, for example, this is the probe for zinc and cadmium detection. This is one for calcium and magnesium detection. So because you need to have good functionalization, we have studied a lot the molecular dynamics of these things. So, for instance, we can model how the polymers wrap around the nanotube. So this is really interesting to understand the physics of that. And also, unfortunately, chemical design is very small science. It's fantastic. Some interactions, so we also have artificial modeling, interaction between chemicals. This is an example with glyphosate. And so glyphosate interacting with one other. So this is the basic development platform. So now, how does it work? Does it work in water? So yeah, in deionized water and in pH buffer, well, it works very well. Example: this is response to nitrate. So this is the pristine CNTs, carbon nanotube, non-functionalized. These are the functionalized carbon nanotube under nitrate exposure. So you put 1,000 ppm of nitrate and you have a great response, and then you go back to 0. It's not exactly 0, but you go back down and then you go back up again. And the FFUR, the functionalized, goes completely the other way. So you have completely different response between the 2 materials. So that's great. And we do this kind of screening for a lot of species: pH, arsenic, chlorine, glyphosate, magnesium, nitrate. And you see very good differentiation between the pristine CNTs and the FFUR. For pH, it's the same, but for arsenic, chlorine, and glyphosate, you have a factor of 2 to 3 of sensitivity difference between FFUR and pristine CNT. And for magnesium and nitrate, it's very strong difference. Actually, magnesium, you have no response to pristine CNT and huge response to FFUR. And nitrate is opposite response. However, this works well with nitrate, but we are completely out of range compared to what the field is. So actually, for nitrate and glyphosate, we don't have enough sensitivity, so let's put this on the side. And we have kept focusing on pH, chlorine, arsenic, and magnesium, where the detection units we have in the lab are compatible with what the World Health Organization requires in terms of water quality. So now, okay, deionized water is fine, but you're going to test in tap water. So tap water, by default, is interference. You just have only interference in tap water. So what we did is we did active chlorine monitoring in tap water under varying pH. So basically, you put bleach in the water, and you increase the bleach level at different pH, which is controlled with formic acid or NaOH, sodium hydroxide. During the measurement, you measure total chlorine and pH. And just for the story, for disinfection, you use the acid part of chlorine, which is epichlorous acid, which is HCNO, which is acid form of chlorine when you put it into the water. To know whether the results are representative, we calibrate on the first experiment, on 2 experiments, one at low pH, one at high pH, and then we apply the results on the following experiment. The sensor, I didn't say sorry, but the sensor are resistant. It's interdigitated electrodes And we are not monitoring directly the resistance. We are monitoring the resistance variation with respect to the baseline. So the delta R divided by R. So it's in percent, the percentage of variation. So this is interesting because even if you have differences in fabrication, you can compare different devices with fabrication differences. And basically, we do a linear calibration model between 0 and 1 milligram per liter of active chlorine. And we have huge sensitivity, 26% per milligram per liter of HClO. This is a very good sensitivity in the field of nanotubes. And this is irrespective of pH and for 3 different sensors. Not the device, the sensor, the sensing unit that you put in the field. What is super important in the field of nanotube, a chronic issue in nanotube is the variability. And actually, less than 15% variability is state of the art for this scale of devices. We have a minimum at 0.5 milligram per liter, which is compatible with the error in measurement. So we can't go below that in this experiment because our experiment is not reliable enough. And we have a detection limit at 0.01 milligram per liter, which again, we can't go further with this experimental design. This is state of the art at this point. There's not that many papers at this state of the art at this point. So this is really good. I should be very happy. I'm not happy because we get completely wrong with pH. We have no sensitivity to pH if you just use a linear model. So you are an active chlorine, and you are so sensitive to chlorine that you don't see the pH anymore. And this is a big problem because my end user, they want pH. Why you don't get pH? And another problem, in that product, you don't see any difference anymore between pristine and FFUR device. So you're, so I'm not going to say a bad word here, but it was a big issue. And actually, what we realized is that the sensitivity in that program of HClO is 10 times the sensitivity to pH. So even the 10 years, the measurement error from your instrument is enough to hide the response to pH. So basically, you have a response to pH, but you don't see it because you have measurement error on chlorine. So you don't know whether you're seeing just an error in chlorine or if you're seeing pH. And actually, what we propose is that we would use a Bayesian formalism to account for measurement uncertainty. So basically, what you do, instead of saying my quantity, my output is X, you're saying my output is X plus measurement error. And what it ends up with is that your measurement, what you measure is bad, but actually your measurement, if you do 100 times the same measurement, you get a cloud of values. And what you do is when you calculate your calibration model, you're not getting one predicted value, you're getting a cloud of values. And if I just do the normal calibration, my prediction is there and my value is there, so my measurement is completely wrong. But if I look at that, my predicted value actually is a cloud of data and it intersects the actual measurement data. So my measurement is good. And so you get, by design, you get the measurement error. You also have calibration rules that include model error. And what is super important is a small data approach. It's not neural network. You don't need thousands of data. This works from 30 data points, which is critical for calibration in water quality because you don't have that many data points. And when you do that, by different methods, you can reach up to 0.25 error in pH, which is basically the measurement uncertainty in this data set that we have. So you can do better than that. So by now, it meets end user expectation. So this brings me to the next stage. So you're happy with the photo and you're sort of happy with the photo, so you can test in the field. And we have this big facility which simulates a city. And basically, it's a small district that you can place within this chamber. And in this chamber, you can control temperature, relative humidity, sun, rain. You could gas. You have a water network inside, and you have also a geothermal structure below the sun. And when you do that, you can test your sensor in the actual water pipe. So these are the two sensors instead into the pipe. And this is real-time data gathering. So this is the USB version. So I just plug in a USB cable into the computer. I can run this at home. I actually did run this at home. You can run this in the facility. And this is the real-time response. So you see the sensor. This is the conductivity sensor responding to chemicals. And this is the response of the FHUR sensor. And we have also a cloud-based version of that. So you can get the data through dashboard and so on. This is classical, but it's not easy to do. You've got to do. Anyway, you see the product where in field condition you have a huge amount of noise. Classic. And we still are fighting through this noise issue. But my PhD student did kill the data to death to get good results. So this is example when the flow is on, you see a kind of noise we're getting. We have this is for the temperature sensor. You see a doubling of the signal line, which is really annoying, which you don't get when the flow is on. And after real time, so we did data processing offline, but it's a data processing that can be done online. So you could apply it in real time. You get a very good calibration, error of 0.2 degree in temperature if it's perfect for what you need, and even 0.1 without. So this is very good. Now it's time to move to air quality monitoring because I'm soon to be out of time. So this is actually work we did with a project with actually Hamida about air quality sensor with resonator. Hamida still developed microwave sensor with functionalization with PEI, and you will have more detail on this tomorrow morning. Or so here something basic so we can understand the rest. So basically, you put two resonators, one without functional material, so reference resonator, and one with PEI material, and you're subtracting the two systems. And you're monitoring the resonance frequency of the system. So this is the PEI, the epoxy-butane PEI. This is what it looks like. And you're looking at the evolution of the resonance frequency as a function of relative humidity. Okay? So far, so good. It works well. And actually, if you characterize in the lab, you have a very clean exponential trend. So you have the frequency depends as an exponential of the relative humidity. To be honest, exponential is not a perfect trend. You prefer linear sensor because you will have trend at low RH value. So basically, you have low sensitivity at low RH and very high sensitivity at high RH. But still, so this works in the lab. And in the lab, you also have a temperature dependence, which is standard that you have. So now what about the field? So we put this sensor in Sensity and we compare its measurement to the response of analyzer, so reference analyzer for gas, CO2, CO, NO2, NO, and ozone. These are gas represented related to traffic issue, exhaust gas. So they are relevant for this kind of application. And this is the signal you get, the frequency difference between the two sensors over 7 days. So this is 7 days duration expressed in minutes, I think. Sorry for the music. So it's 7 days of data. So you see, at least the sensor is covering the day variation, so that's good. What is less good is that this, when you correlate this with a value from O3, from NOx, from CO2, from RH, you have very strong correlation. So are you sensing RH, relative humidity? Or are you sensing O3 or NOx or CO2? Okay? That's the question. And the answer to that is, again, with Bayesian calibration. So we use the same method I talked about before, and we calibrate for humidity with and without calibrating for the other gas at the same time. So do you improve the calibration if you take into account the other gas? Actually, after working the data to death, the best result is just when you calibrate for humidity. You have no improvement at all when including over interference, which for us means that the main trend is humidity and you have no interference. And this is actually pretty good news. It's pretty rare to have a sensor score on humidity, which is 4%, so it's not great, but if it's interference-free in real conditions, it's good news. What you see here is the response. Actually, you see the sensor is not very good at low value of humidity, because at low value of humidity, it's less sensitive. So the graphic I showed before, so it makes sense that you are less sensitive. At high humidity, you are very well. And this color shift shows the uncertainty around the value. I told you we can get the uncertainty assessment, so that's what is noted there. The 2 sigma uncertainty spread. So why did we see correlation in the previous graphic? It's simply because temperature, reactivity, and the gas are correlated by chemical reasons over the day, and that's why we see that. And if you do the instrumentation over a longer period of time, some of this correlation diminishes because you have climatic and gas difference over time. So now my last slide, I have 20 seconds, so that's great. This is now when you go to real life. Another problem that happens is that sensor drift. I don't know any single sensor that will not drift over time from the technology you have today, and even an analyzer are going to drift. So what people are doing today is they do in-situ calibration, which means calibrating the sensor and leaving them in the field. So I won't have time to go in detail on that, but I can refer you to a review paper from my student Laporte 2 years ago, where he analyzed all the in-situ calibration algorithms. And the story, in short, is that you have a bunch of methods that are based on having a reference nearby. So that's close to calibration, and if you have a reference, you compare the value to the reference. So that's great. And you have a bunch of methods which are blind calibration. So you say if you put enough sensor and you let them look together, they will magically find the right value because of math. And the math are very good for math, and it should work. And what we did is we did a calibration algorithm. We evaluated the performance of these different algorithms on realistic data sets. And even if you change very simple pollutant model, they fail. A Gaussian model fail with this algorithm. So the message there is that calibration, instant calibration will work, but if you want to use instant calibration, you have to validate your algorithm on a representative data set to make sure it works in your use case. So I'm finishing on that. Just putting my conclusion on the board. You can read them because I have to understand, and I can take your questions because I have time. Okay, thank you so much.
Very much, Bérengère, for this really nice talk. So, any questions, please?
So, what would you ask data analysis person or a hardware person to help? Because you know all the data analysis. So you need something better. I know that. So what's it?
From the data analytics point of view?
Right, but you listen to me because I'm asking you to improve my sensor. So what unmet needs in data analysis tools you would like data analysis people to improve for you?
Okay, right now, okay. I will say as I'm more of a data person and working with data analytics as myself. Okay. For me, I'm not very old, but from the time we didn't learn AI at school. So I'm catching up on AI tools and so on. And there's no transparency on what will work and not work. So I mean, the tools are either a black box or very sophisticated, and it's very hard to get that. So you find what you cannot do. So I have a colleague that is very strong, so you can develop his own algorithm, and that's what we did in that case. But what I see very often is just you got your student, and your student is just running through the algorithm. And just, okay, Google tells me I take this algorithm and I take the next one and then the next one and see what works. And I like to have better than that to understand why an algorithm is going to work.